Right now, as you listen to these words, you're traveling through time, moving into the future at a rate of 1 second per second. Now, this might seem obvious, even trivial, but it is actually one of the deepest mysteries in all of physics. And here is something remarkable that most people do not realize. According to Einstein's theories, you could change how fast you travel through time. If you moved fast enough or sat near a strong enough gravitational field, time would pass differently for you than for everyone else on Earth. Astronauts on the International Space Station age slightly slower than people on Earth, returning home younger by tiny fractions of a second than they would otherwise be. Particles in accelerators live longer when moving near the speed of light, their internal clocks running slow compared to stationary particles. It is not science fiction, not speculation, not a dream. It is established physics confirmed by countless experiments over the past century. Time travel to the future is not just possible, it is happening right now, all around us, in small ways. Welcome to the Drowsy Astronaut, where tonight we explore one of humanity's oldest dreams, the possibility of traveling through time itself. I'm glad you're joining us here tonight, settling in from wherever you may be listening. And I invite you to let go of the day as we wander through these ideas together, allowing the story to unfold gently at its own pace. If this helps you relax and drift towards sleep, consider subscribing, but for now, just settle in and let the journey begin. The dream of time travel is ancient, appearing in myths and stories for thousands of years, from tales of people who slept for centuries and woke in a changed world. Rip Van Winkle, the Seven Sleepers, King Muchukunda, cultures around the world have imagined what it would be like to leap through time. But for most of history, time travel was pure fantasy, a pleasant story with no connection to how the universe actually works. That changed in 1905 when a young patent clerk named Albert Einstein published a paper that would revolutionize our understanding of time. Einstein showed that time is not what we thought it was, not a fixed background against which events play out uniformly everywhere. Instead, time is flexible, stretchable, woven together with space, forming a fabric that can bend and warp and flow at different rates. This discovery opened the door to serious scientific study of time travel, turning a fantasy into a question that physics could address. What was once purely imaginative became a matter of equations and experiments, a puzzle that the greatest minds of the 20th century would grapple with. Tonight we will explore what physics tells us about time travel, separating what is possible from what is probable, from what seems impossible. We will learn how traveling to the future already works in principle, and why traveling to the past is far more problematic. We will encounter wormholes and rotating black holes, cosmic strings and closed time-like curves, exotic structures that might, in theory, allow journeys backward through time. And we will consider the paradoxes that arise when we imagine changing the past, puzzles that have troubled physicists and philosophers alike. The question of whether time travel is possible touches something deep in human nature, our longing to revisit the past or glimpse what the future holds. We all have moments we wish we could relive, decisions we wish we could change, people we have lost whom we would give anything to see again. The past calls to us with its mixture of joy and regret, and the future beckons with its promise and uncertainty. Time travel speaks to these longings, offering a fantasy of control over the river that carries us forward. But there is also something peaceful about accepting the flow of time, about resting in the present moment rather than straining toward past or future. Tonight we will hold both perspectives gently, the wonder of imagining time travel and the peace of accepting time as it is. The physics itself is beautiful, regardless of practical applications, revealing deep truths about the nature of reality, and contemplating these truths can bring a kind of serenity, a quiet appreciation for the strangeness and elegance of the universe. To understand time travel, we first need to understand time itself, and this is where our journey truly begins tonight. What is time? Why does it flow? Why does it seem to move in only one direction? These questions have puzzled thinkers for millennia. The answers that physics provides are surprising and counterintuitive, overturning common sense assumptions we hold without even realizing it. Time is not what it appears to be, and understanding its true nature is the first step toward understanding time travel. We experience time as a river carrying us forward, always forward, from past through present toward an unknown future. We remember the past, but not the future. We can act to change the future, but not the past. And every moment slips away as soon as it arrives, replaced by the next. This experience feels so fundamental, so obviously true, that we rarely question whether it reflects the actual nature of reality. But physics suggests that our experience of time might be misleading, a partial view of something far stranger and more wonderful. Isaac Newton believed time was absolute, ticking uniformly everywhere, a cosmic clock that all observers could agree on. In his universe, if 1 hour passed for you, 1 hour passed for everyone, regardless of how fast you were moving or where you were in space. This seemed intuitively obvious and matched everyday experience. So for centuries, it was the foundation of physics. But Einstein discovered that Newton was wrong, that time is relative, varying from observer to observer in ways that can be measured. The key insight came from thinking about the speed of light, which experiments showed was the same for all observers regardless of their motion. This seems paradoxical at first. How can light travel at the same speed, relative to someone standing still and someone moving toward it? The answer is that time itself adjusts to make this work, stretching and compressing differently for different observers. A moving clock runs slower than a stationary clock, and this effect, called time dilation, has been confirmed countless times. This means that time travel to the future is built into the structure of reality, a consequence of how time actually works at a fundamental level. If you could travel close to the speed of light, time would slow dramatically for you, and you could journey years into Earth's future while aging only days or weeks. You would arrive in a world transformed, everyone you knew older or gone, a genuine traveler through time, displaced from your original era. This is not speculation, but established physics, guaranteed by equations that have never failed a test. Traveling to the past is a different matter entirely, raising problems that range from the practical to the seemingly impossible. The laws of physics as we understand them do not obviously forbid backward time travel, but they do not obviously allow it either, and paradoxes lurk everywhere. If you could travel to the past and change something, you might prevent the very events that led to your time travel. These paradoxes suggest that either backward time travel is impossible, or the universe has subtle mechanisms to prevent contradictions. Tonight, we will explore all of this slowly and peacefully, letting each concept settle before moving to the next. There is no rush, no test at the end, No need to remember every detail. Just the gentle pleasure of contemplating one of nature's deepest mysteries. Time travel is a doorway into understanding time itself, and understanding time changes how we experience every moment of our lives. So let us begin this journey through the fabric of time, exploring what physics tells us about one of humanity's oldest dreams. The scientists who study time travel are not cranks or dreamers. They are among the most brilliant physicists of our age. Stephen Hawking worked on time travel, as did Kip Thorne, both giants in the field of general relativity and gravitational physics. Richard Feynman considered related questions in quantum mechanics, and John Wheeler pondered the nature of time throughout his long career. These are serious people asking serious questions, not about building machines necessarily, but about what the laws of physics allow. What they have found is subtle and surprising, neither a simple yes nor a simple no to the possibility of time travel. The future seems accessible, at least in principle, through high-speed travel or strong gravity, while the past remains elusive, guarded by paradoxes and perhaps by the laws of physics themselves. Wormholes might theoretically connect different times, but require exotic matter we have never observed. And rotating black holes might offer passages, but would likely destroy anything that entered. The picture is complex, full of theoretical possibilities and practical impossibilities intertwined. As we explore these ideas in the parts ahead, let the strangeness become familiar, let the impossible become at least imaginable. We will build up understanding step by step, from basic concepts of time through Einstein's revolutions to the exotic physics of wormholes. Each piece will connect to the next in a journey through human understanding, a story of how we came to ask these questions and what we have learned. And through it all, we will maintain a sense of peace and wonder, resting in the contemplation of deep ideas. The night is long enough for this journey, and there is no need to hurry. Before we can travel through time, we need to understand what time actually is. And this turns out to be one of the most difficult questions in all of philosophy and physics. We all experience time. We live in it every moment of every day. Yet when asked to define it, we find ourselves grasping at something that slips away. St. Augustine captured this perfectly 16 centuries ago, saying that if no one asks him, he knows what time is, but if asked to explain it, he does not know. Our everyday experience of time seems obvious and straightforward. One moment follows another in a steady procession from past to future. We wake in the morning and the day unfolds, hour by hour, until night comes and we sleep and wake to a new day. We remember yesterday, but not tomorrow. We plan for next week, but cannot revisit last week. And through it all, time seems to carry us forward like a river. This experience is so universal, so constant, that we rarely question whether it reflects the true nature of time. Clocks measure time by counting regular, repeated motions. The swing of a pendulum, the vibration of a quartz crystal, the oscillation of atoms. We agree to synchronize our clocks and divide the day into hours and minutes, creating a shared framework for coordinating our activities. This works wonderfully for practical purposes, for catching trains and meeting friends, but it tells us nothing about what time actually is. The clock measures intervals of time, but what is the substance being measured? What is this thing that the clock divides into equal parts? One view, dominant for centuries, was that time is like a container, an invisible stage on which events play out, existing independently of those events. Isaac Newton held this view. describing absolute time that flows uniformly, regardless of what happens in the universe or whether anything happens at all. In Newton's picture, time would exist even in an empty universe, ticking away, whether or not there were any clocks or observers to measure it. This seemed intuitive, matching our sense that time is simply there, a background against which the drama of existence unfolds. But there were always puzzles with this view, questions that troubled philosophers, like whether empty time before the universe would be meaningful. If nothing exists to change, does it make sense to say time is passing? Or is time inseparable from the events that occur within it? These questions remained largely philosophical until Einstein arrived and showed that Newton's absolute time was not just philosophically questionable, but physically wrong. Time is not a fixed background. It is flexible and relative, depending on how observers move through space. Einstein discovered that there is no universal now, no single present moment, shared by all observers throughout the universe. Two events that seem simultaneous to one observer might occur at different times according to another observer moving differently. This is not an illusion or a trick of measurement. It reflects the genuine structure of space-time, the arena in which physics occurs. There is no cosmic clock ticking uniformly for everyone, only local times that depend on motion and gravity. This relativity of time has profound implications for how we think about existence, suggesting that past, present, and future might all be equally real. If different observers disagree about what is happening now, then the present moment has no special status in physics. What I call now might be your past or your future, depending on how we move, and neither perspective is more correct than the other. This leads to the block universe view, where all of time exists at once, like a frozen four-dimensional sculpture. In the block universe, the Big Bang is not gone and the far future has not yet to come. They both exist, just at different locations in the four-dimensional block. Your past selves still exist at earlier points in the block, and your future selves already exist at later points. This view is controversial, and not all physicists accept it, but it emerges naturally from taking Einstein's relativity seriously. If it is true, then in some sense, every moment of time is eternal, existing forever in the unchanging block of space-time. But if the block universe is real, why do we experience time as flowing? Why does the present seem special and the past feel gone? This remains one of the deepest unsolved problems in physics and philosophy. The question of why consciousness seems to move through time. Physics describes a static block, yet we feel ourselves progressing, from moment to moment, always in the present, never in the past. This disconnect between physical description and lived experience is sometimes called the problem of the arrow of time. The arrow of time points only one way, from past to future, and this asymmetry pervades our experience and much of physics. Eggs break but do not unbreak. Ice melts but does not spontaneously freeze. And we remember yesterday but not tomorrow. This directionality comes from the second law of thermodynamics, which says that entropy, a measure of disorder, always increases overall. The past had lower entropy, the future will have higher entropy, and this gradient gives time its arrow, its sense of direction. But here is something strange. The fundamental laws of physics are almost all time symmetric, meaning they work equally well run forward or backward. If you filmed atoms bouncing and played the film in reverse, the reversed motion would also obey the laws of physics perfectly. There is nothing in the basic equations that prefers forward time to backward time, yet our experience and the macroscopic world show a clear direction. The arrow of time seems to emerge from special initial conditions, the low entropy state of the Big Bang, rather than from the laws themselves. This has implications for time travel, because if the laws are time-symmetric, then there is no fundamental prohibition on traveling backward in time. The arrow of time might be a statistical effect, an accident of initial conditions, rather than a deep law forbidding backward journeys. Of course, this does not mean backward time travel is easy or even possible, just that the asymmetry of time is subtler than it first appears. Understanding the arrow of time is crucial for understanding what barriers might prevent or allow travel to the past. We also need to ask whether the past and future still exist in any meaningful sense, whether there is somewhere to travel to when we speak of time travel. If only the present moment exists and the past has vanished, then traveling to the past would mean traveling to nothing, which makes no sense. But if the block universe is correct, and all times exist eternally, then past moments are real places, and travel to them becomes at least conceptually possible. The metaphysics of time matters, for whether time travel is coherent as an idea. Some physicists and philosophers adopt presentism, the view that only the present is real, that the past existed but is gone and the future does not yet exist. On this view, time travel to the past would indeed be incoherent because there is no destination for the time traveler to reach. Others adopt eternalism, the block universe view, where all times are equally real and time travel becomes at least imaginable. The debate continues, with arguments on both sides and no consensus resolution. What we can say with confidence is that time is deeply strange, far stranger than our everyday experience suggests. It is not a fixed background, but a dynamic part of reality, woven together with space into the fabric called spacetime. It runs at different rates for different observers, and its apparent direction might emerge from contingent facts rather than fundamental laws. Understanding these features of time is essential for making sense of the physics of time travel that we will explore. As you rest with these ideas, let the mystery of time settle gently, like a question that does not demand an answer tonight. We have lived in time our whole lives without understanding it, and we can continue to live in it peacefully without full comprehension. The mystery is part of what makes existence beautiful, a reminder that reality runs deeper than our understanding. Time carries us forward, and we can trust that flow even as we wonder about its nature. In the next part, we will explore Einstein's first great revolution, special relativity, and how it changed our understanding of time forever. In 1905, a 26-year-old patent clerk in Switzerland published 4 papers that would transform physics forever. His name was Albert Einstein, and he was working at the Swiss Patent Office, evaluating technical applications while thinking about the deepest questions in physics. He had no university position, no laboratory, no famous mentors, just a brilliant mind and the courage to question assumptions everyone else took for granted. That year would later be called his miracle year, producing work that would make him the most famous scientist in history. One of those papers introduced special relativity, a theory that would overturn Newton's ideas about space and time. Einstein began with 2 simple principles that seemed obviously true, and followed their logic to conclusions that seemed obviously impossible. The first principle was that the laws of physics are the same for everyone, regardless of how fast you are moving, as long as your motion is uniform. The second principle was that the speed of light in a vacuum is constant, the same for all observers, no matter how they are moving, relative to the light source. These two principles seem innocent enough, almost trivial. But when you think through their consequences carefully, paradoxes seem to arise. Imagine you are standing still and a beam of light passes you, traveling at about 300,000 kilometers per second. Now imagine someone zooming past you at half the speed of light in the same direction. Surely the light would appear slower to them, like a car seems slower when you chase it. But Einstein's second principle says no, the light is still moving at the same speed, the same 300,000 kilometers per second relative to the moving observer too. How can this be? How can the same light beam move at the same speed, relative to two observers moving differently? The answer is that time and space themselves adjust to make it work, stretching and compressing in ways that keep the speed of light constant. Time runs slower for the moving observer compared to the stationary one, and lengths contract in the direction of motion. These effects are real, not illusions, and they have been confirmed by countless experiments since Einstein proposed them. The slowing of time for moving observers is called time dilation, and it is the key to understanding time travel to the future. The faster you move relative to another observer, the slower your time runs, compared to their time as they would measure it. At everyday speeds, this effect is tiny, far too small to notice. But as you approach the speed of light, it becomes dramatic. At 90% of light speed, your time runs at less than half the rate, and at 99%, it runs at about 1/7 the rate. This means that if you traveled in a spaceship at very high speed, you would age much slower than the people you left behind on Earth. You might travel for what feels like a year to you, while decades pass on Earth during your journey. When you returned, you would find yourself in Earth's future, having skipped over years or decades of Earth time. You would be a time traveler, genuinely displaced from your original time, not through any exotic mechanism, but simply through the physics of high-speed motion. This effect leads to the famous twin paradox, a thought experiment Einstein considered, involving identical twins who experience different amounts of time. One twin stays on Earth while the other travels to a distant star, moving at close to light speed for the outward and return journey. When the traveling twin returns, they are younger than their sibling, having aged less during the journey due to time dilation. The twin who stayed home might be elderly, while the traveler is still young, separated by years or decades of differential aging. Is this really time travel, or just differential aging? Does the traveling twin truly move into the future? The answer is yes. In every meaningful sense, they have time traveled, arriving at a moment in Earth's history that they would not have reached by staying home. They have skipped over years of Earth time, jumping ahead, as real a journey through time as any science fiction story imagines. The only difference is that it is a one-way trip. You can travel to the future, but not use this method to return to the past. The twin paradox bothered many people when Einstein first proposed it, because it seemed to violate the symmetry that special relativity was supposed to embody. If all motion is relative, why is one twin younger than the other? Why is the traveling twin special if motion is symmetric? The answer is that the traveling twin accelerates to turn around and come back, and acceleration breaks the symmetry between the two twins. The twin who accelerates experiences less time, and this is consistent with the principles of special relativity. We have actually tested time dilation directly with atomic clocks, putting incredibly precise clocks on airplanes and comparing them to clocks on the ground. The flying clocks run slightly slower, exactly as Einstein predicted, confirming that time dilation is not just theoretical, but experimentally real. These experiments have been repeated many times with increasing precision, and the results always match Einstein's equations to many decimal places. Time dilation is as well established as any fact in physics, a foundation of our understanding of how the universe works. Particle accelerators provide even more dramatic confirmation of time dilation when particles are accelerated to near light speed and their lifetimes are measured. Muons, for example, are particles that decay very quickly when at rest, lasting only about 2/millionths of a second before transforming into other particles. But when muons are accelerated to 99% of light speed, they last much longer as measured by laboratory clocks. Their internal clocks are running slow due to time dilation, and they survive long enough to be detected far from where they were created. The cosmic rays that constantly bombard Earth provide natural confirmation because muons created high in the atmosphere reach the ground. If muons decayed at their normal rest frame rate, they would disappear long before reaching the surface from their creation altitude. But because they are moving so fast, their time is dilated and they survive the journey to be detected by physicists on the ground. Every muon that reaches us is a tiny time traveler, experiencing far less time than we do during its brief existence. So time travel to the future is not speculative or uncertain. It is established physics that we have verified experimentally. The only questions are practical ones about how to achieve high enough speeds and whether the energy requirements are feasible with any conceivable technology. We will explore these practical challenges in a later part, but for now, just appreciate that the physics is solid and well understood. Einstein showed us that time travel to the future is woven into reality, a consequence of how time actually works at a fundamental level. Special relativity also revealed that space and time are not separate things, but aspects of a single entity called spacetime that has 4 dimensions. Just as a shadow on the ground depends on how an object is oriented in 3 dimensions, measurements of space and time depend on how observers move through 4-dimensional spacetime. What one observer measures as purely spatial distance, another observer moving differently measures as partly time interval. Space and time mix together, converted into each other by the transformation between moving reference frames. This unification of space and time was made explicit by Hermann Minkowski, Einstein's former mathematics teacher who developed the geometric interpretation of special relativity. Minkowski famously declared that henceforth space by itself and time by itself are doomed to fade into mere shadows, and only a union of the two will preserve independent reality. This geometric view of space-time became essential for Einstein's next great theory, general relativity, which would bend and warp this unified space-time. The stage was set for even deeper revelations about how gravity affects time and opens further possibilities for time travel. Special relativity showed that time is flexible, running at different rates for different observers, but the variations depend only on relative motion, not on gravity or acceleration. Einstein knew this was incomplete because gravity also affects motion and should therefore affect time. It took him another 10 years to work out the full theory, the general theory of relativity that would incorporate gravity into the picture. When he succeeded, the results were even more surprising. showing that gravity itself bends time in ways that might allow even stranger possibilities. For now, rest with the knowledge that time travel to the future is real, a consequence of Einstein's special relativity, confirmed by experiment. The future is accessible, at least in principle, through high-speed travel, and every fast-moving particle is a time traveler, skipping ahead through time. We have not built practical time machines yet, but the physics tells us that nature allows this kind of journey. In the next part, we will explore Einstein's general relativity and how gravity bends time in ways that deepen the mystery further. Special relativity was just the beginning of Einstein's revolution, because it only described what happens in the absence of gravity. But gravity is everywhere in the universe, holding planets in orbit around stars, binding galaxies together across millions of light years of space. Einstein knew that his theory was incomplete until it could incorporate gravity, and he spent 10 years struggling to extend special relativity into this more general domain. The result, published in 1915, was general relativity, perhaps the most beautiful theory in all of physics. The key insight of general relativity is that gravity is not really a force, pulling objects toward each other across empty space as Newton imagined. Instead, gravity is the curvature of space-time itself, caused by the presence of mass and energy in a region. Massive objects like the Sun curve the space-time around them, and other objects like Earth follow this curvature, moving along the straightest possible paths. What we experience as the force of gravity is actually the geometry of space-time guiding our motion. Einstein summarized this with a poetic phrase: "Matter tells space-time how to curve, and space-time tells matter how to move." The Sun does not reach out and pull the Earth with invisible strings. Instead, the Sun bends the space-time around it into a curved shape. The Earth, moving through this curved space-time, follows a path that we observe as an elliptical orbit around the Sun. There is no force acting at a distance, only the local geometry of space-time determining how objects move. This geometric view of gravity has been confirmed by many observations, including the bending of starlight as it passes near the Sun. During a solar eclipse in 1919, astronomers measured starlight positions and found they were shifted exactly as Einstein's equations predicted from the Sun's bending of spacetime. This confirmation made Einstein world famous overnight and established general relativity as the correct theory of gravity. But general relativity also has profound implications for time, because space-time curvature affects the flow of time, not just the paths of objects. Time runs slower in stronger gravitational fields, so clocks near massive objects tick more slowly than clocks farther away. This gravitational time dilation is separate from the velocity-based dilation of special relativity, and it has been directly measured with atomic clocks at different altitudes. A clock on a mountain runs faster than an identical clock at sea level, because the mountaintop clock is farther from Earth's center in weaker gravity. This effect is small on Earth, just a few microseconds per year difference, but it is real and has practical consequences for technology. The GPS satellites that guide your phone and your car must correct for gravitational time dilation to give accurate positions. The satellites orbit high above Earth, where gravity is weaker, so their clocks run slightly faster than clocks on the ground. Without accounting for this effect, GPS positions would drift by kilometers per day, so relativistic corrections are built into the system. Every time you use GPS, you are relying on Einstein's general relativity, trusting that his equations correctly describe how gravity affects time. The effect becomes more dramatic near more massive objects, and near black holes, it becomes extreme. A black hole is a region where gravity is so strong that nothing can escape, not even light, which is why they appear black against the sky. As you approach a black hole, the gravitational time dilation increases, and time runs slower and slower compared to observers far away. At the event horizon, the boundary of no return, time appears to stop completely from the perspective of a distant observer. Imagine watching a brave astronaut falling toward a black hole from your safe vantage point far away in space. You would see them slow down as they approach the horizon, moving more and more slowly as time dilation increased. Their signals would be redshifted, stretched to longer wavelengths, their voice dropping to lower and lower pitches. You would never quite see them cross the horizon, their image frozen at the edge, fading and reddening over time. From your perspective, they would take an infinite time to fall in, stretched out by gravitational time dilation to an eternal approach. But from the astronaut's own perspective, the experience would be very different. They would cross the horizon in a finite amount of their own time. They would not notice anything special at the moment of crossing. No boundary or barrier, just continued falling toward the center. The inside of the black hole would be their future, a region of spacetime from which they could never return. The extreme time dilation means that what seems like moments to them could be eons to observers outside, watching and waiting. This is time travel of a sort, though not the kind science fiction usually imagines. Not a controllable journey to a specific date in the past or future. By spending time near a black hole and then escaping if possible, you would return to find that much more time had passed outside. You would have jumped into the future like the traveling twin, but through gravitational dilation rather than high-speed motion. In principle, you could use a black hole as a time machine to the future, if you could somehow survive the journey and escape again. General relativity describes space-time as a dynamic entity, curved and warped by matter. And this opens possibilities that flat Newtonian space never allowed. If space-time can be bent, perhaps it can be bent in extreme ways, creating loops or tunnels or bridges that connect different regions. Perhaps it could be bent enough to connect different times, allowing travel not just to the future, but to the past as well. These exotic possibilities emerge from Einstein's equations, though whether they can be realized in our universe is another question. The mathematics of general relativity is expressed in Einstein's field equations, a set of 10 coupled differential equations that relate curvature to matter and energy. These equations are notoriously difficult to solve, but physicists have found many exact solutions describing different situations. Some of these solutions describe ordinary things like stars and planets, while others describe exotic structures like wormholes and rotating universes. It is in these exotic solutions that the possibility of backward time travel begins to appear. We will explore some of these solutions in later parts, wormholes and rotating black holes and cosmic strings that might allow time travel. For now, the important point is that general relativity allows time to be affected by gravity, running slower in stronger fields, bending along with space. This is not speculation, but tested physics, confirmed by atomic clocks and GPS satellites and observations of stars near black holes. The fabric of space-time is flexible, and gravity shapes both the space we move through and the time we experience. There is something profound about living in a universe where time is not fixed, where the flow of time depends on where you are and how gravity curves the space around you. We tend to think of time as universal, the same everywhere, but Einstein showed that this is just an approximation, valid only when gravity is weak and uniform. In the real universe, time is local, different, at different locations, running at different rates, near different masses. Every planet, every star, every galaxy has its own pace of time, shaped by its gravitational field. This means that the universe is full of differential time, with some regions aging faster than others in a cosmic patchwork. The cores of stars, where gravity is intense, tick more slowly than the outer layers floating above. The centers of galaxies, anchored by supermassive black holes, are younger than their outskirts in terms of elapsed proper time. This is not metaphor or approximation. It is the literal truth of how time works in Einstein's universe. As you rest now, consider that the atoms in your body are experiencing slightly different rates of time depending on their position. The atoms in your feet, closer to Earth's center, are in slightly stronger gravity than the atoms in your head. The difference is minuscule, a few femtoseconds per year, but it is real and could be measured with sensitive enough clocks. You are a tapestry of different times, woven together into a coherent experience by your conscious mind. In the next part, we will explore how these effects could be used to build a time machine that travels to the future. We have established that time runs at different rates depending on motion and gravity, and now we can ask whether this allows genuine time travel to the future. The answer is yes, unambiguously. The physics is clear. Traveling to the future is possible, in principle, using methods we already understand. The only obstacles are practical, matters of engineering and energy, not fundamental prohibitions built into the laws of physics. Tonight we explore how a future time machine might work, and consider the challenges of actually building one. The simplest approach is the one Einstein revealed with special relativity. Travel at very high speed, and your clock runs slower than clocks left behind. If you could travel at 90% of the speed of light, every year that passes for you would see about 2.3 years pass on Earth. At 99% of light speed, the ratio is about 7:1, so a year of your time would see 7 years pass at home. At 99.9% of light speed, the ratio is over 20:1, and at even higher speeds, the dilation becomes more extreme still. Let us imagine a hypothetical journey to a nearby star, Alpha Centauri, about 4 light-years from Earth. At 50% of light speed, the journey would take about 8 years each way, and time dilation would be modest, saving you only a bit of time. But at 97% of light speed, though the journey still takes about 4 years, your onboard clocks would show only about 7 months for each leg. You would return after a round trip of about 14 months of your time to find 8 years had passed on Earth since your departure. At even higher speeds, the effects become dramatic, approaching the ultimate time machine that special relativity allows. Imagine traveling at 99.9% of light speed to a star 100 light-years away and back. The journey would take about 200 years from Earth's perspective, but your clocks would show only about 3 years had passed. You would return to an Earth 2 centuries in the future, having aged only 3 years during the voyage through space and time. The current record holder for human time travel is the cosmonaut Sergei Krikalev, who spent over 800 days in orbit on space stations over his career. The International Space Station orbits at about 7.7 kilometers per second, fast enough to create measurable time dilation compared to Earth's surface. Krikalev returned from his cumulative time in space about 1/50th of a second younger than he would have been if he had stayed on Earth. This is tiny, but it is real time travel, a genuine skip into Earth's future caused by his high-speed motion. Astronauts also experience a counteracting gravitational effect, because in orbit they are farther from Earth's center, in weaker gravity. This would make their clocks run faster, partially offsetting the velocity effect. But for low Earth orbit, the velocity dilation dominates, and astronauts return younger. For higher orbits, the gravitational effect might dominate, and astronauts would return older than if they had stayed home. The interplay of these two effects determines the net time travel experienced by anyone leaving Earth. The practical challenges of high-speed time travel are enormous, centered on the problem of how to accelerate a spacecraft to near light speed. The energy required increases without limit as you approach light speed, because relativistic effects make the spacecraft harder to accelerate the faster it goes. At 90% of light speed, a spacecraft would have twice the energy of its rest mass converted into kinetic energy. At 99%, it would be about 7 times, and at 99.9%, over 20 times, requiring colossal amounts of energy that dwarf anything we can currently produce. To put this in perspective, accelerating a modest spacecraft of 1,000 kilograms to 99% of light speed would require about 6 times 10 to the 19 joules. This is roughly the entire energy output of the Sun for 1 second, or the total energy consumption of human civilization for 1,000,000 years. We are nowhere near being able to produce such energies, and the engineering challenges of containing and directing them are equally daunting. A practical high-speed time machine would require technologies far beyond anything we currently possess. But the physics does not forbid it, and that is the important point. The laws of nature allow time travel to the future through high-speed motion. If a sufficiently advanced civilization could harness enough energy, they could build a working time machine using well-understood physics. The fact that we cannot do it now is a matter of engineering limitations, not fundamental impossibility written into the equations. Future generations, with better technology, might accomplish what seems impossible to us today. There is another approach to future time travel that avoids the need for high speed, using strong gravitational fields to slow time instead. We saw that time runs slower near massive objects, so spending time near a very massive object would let you skip into the future. If you could safely orbit close to a black hole without falling in, time would pass much more slowly for you than for distant observers. After orbiting for what seemed like a year to you, you could return to find centuries had passed elsewhere. The practical challenges here are also immense, because the gravitational forces near black holes would tear ordinary matter apart. The tidal forces, the difference in gravity between your feet and your head, would stretch you into a long, thin strand in a process physicists call spaghettification. Only for very large black holes are the tidal forces gentle enough at the horizon. And even then, the challenge of traveling to such a black hole and returning is enormous. But again, the physics allows it in principle. The challenge is practical, not fundamental. There are also intermediate approaches that might be more feasible, using neutron stars or other compact objects with strong but not extreme gravity. A neutron star is the collapsed core of a massive star incredibly dense with a teaspoon weighing billions of tons. Near a neutron star, gravitational time dilation is significant, though not as extreme as near a black hole. Orbiting such an object for a while would let you travel modestly into the future. What all these approaches share is that they allow travel to the future only. You can skip ahead, but you cannot use these methods to return. Once you have traveled a year while Earth aged a century, you are stuck in that future with no way back. This is a fundamental asymmetry in the physics of time travel. The future is accessible, but the past is guarded by different rules. Whether backward time travel is possible at all requires exploring more exotic physics, which we will do in later parts. Time travel to the future has been verified at small scales, with atomic clocks and particle accelerators confirming Einstein's predictions. The effects are real, measurable, and well understood, differing from science fiction only in the magnitude we have achieved so far. Every GPS satellite is a time traveler. Every fast-moving muon is a time traveler. And in a sense, every object in the universe is traveling through time at its own rate. The universe is full of differential time, a patchwork of different rates stitched together by the fabric of space-time. Consider for a moment the strange implication of this physics, that the future already exists in some sense, waiting for us to arrive. If you could travel at near light speed and return centuries hence, those centuries would not be created by your journey but uncovered, revealed. This connects to the block universe view, where all of time exists eternally, and we merely traverse it. Your time travel would be a shortcut through the block, a path that skips over regions others must cross slowly. Whether the block universe is literally true remains philosophically debated, but the physics of time, dilation, strongly suggests that future moments exist. Your future self, in some sense, is already there, waiting at a later location in the four-dimensional block of space-time. This is a strange thought, perhaps unsettling to some, but there is also peace in it, a sense of existence as complete and whole. The journey is already laid out, and we travel it in the only way we can, moment by moment. In the next part, we will turn to the more challenging question: whether travel to the past is possible, and what obstacles it faces. We have seen that traveling to the future is allowed by physics, well understood and experimentally confirmed through time dilation and gravitational effects. But what about the other direction, traveling to the past, revisiting moments that have already occurred, perhaps even changing them? This is where the physics becomes murky and the problems multiply, where paradoxes arise that seem to forbid backward time travel entirely. Tonight we explore why the past is so much harder to reach and what barriers physics might place in our way. The first and most obvious problem is the arrow of time, the fact that time seems to flow in only one direction throughout the universe. We remember the past but not the future. We see causes before effects, and entropy always increases, disorder growing as time moves forward. This asymmetry is built into our experience at the deepest level, and traveling backward would seem to violate everything we know about how time works. The past feels gone, vanished, no longer existing, while the future feels like an open space waiting to be filled. But as we discussed earlier, the fundamental laws of physics are mostly time-symmetric, meaning they work equally well run, forward or backward in time. The arrow of time seems to emerge from special initial conditions, the low entropy state of the Big Bang, rather than from the laws themselves. This suggests that backward time travel might not be fundamentally forbidden, just extraordinarily difficult, going against the statistical grain of the universe. The laws do not say you cannot unshuffle a deck of cards, just that it is vanishingly unlikely to happen spontaneously. However, backward time travel faces a much more serious problem than entropy: the problem of paradoxes that seem to create logical contradictions. The most famous is the grandfather paradox, which asks what happens if you travel back in time and prevent your own grandfather from meeting your grandmother. If you succeed, your parent would never be born, and neither would you. But then who traveled back in time to prevent the meeting? You seem to be both existing and not existing, a logical impossibility that makes no sense. This paradox applies to any attempt to change the past in a significant way, creating a contradiction between the past you came from and the past you create. If you stop a war, who remembers to travel back and stop it? If you save a life, what motivates future you to make the journey? The very success of your mission seems to erase the reason for your mission, creating a loop that feeds back on itself in contradictory ways. These paradoxes suggest that backward time travel might be logically impossible, not just difficult but incoherent as a concept. Some physicists take these paradoxes as proof that backward time travel is impossible, that nature must somehow prevent it to maintain logical consistency. This view has been championed by Stephen Hawking, among others, who proposed what he called the chronology protection conjecture to this effect. The idea is that whenever physics seems to allow time travel to the past, some mechanism intervenes to close the loophole and preserve causality. The universe, in this view, protects itself from paradoxes, ensuring that the past remains fixed and unchangeable. But other physicists have proposed ways that paradoxes might be avoided or resolved, allowing backward time travel without logical contradiction. The most famous is the Novikov self-consistency principle, named after the Russian physicist Igor Novikov, who developed it. This principle says that any event that might cause a paradox has zero probability of occurring, enforced by the laws of physics. You could travel to the past, but you could not do anything. That would create a contradiction with the history that led to your journey. Under the Novikov principle, if you tried to kill your grandfather, something would always prevent you, some coincidence or accident or failure. Your gun would jam, you would slip and fall, you would have the wrong address. The universe would conspire to maintain consistency without forbidding time travel. This sounds like magical protection, but it might emerge naturally from the requirement that physics be self-consistent across time loops. Only self-consistent histories are allowed, and the laws of physics enforce this consistency automatically. Another proposed resolution involves parallel timelines or branching universes, where changes to the past create a new timeline rather than altering the original. In this view, if you travel back and change something, you create a branch where the change occurred, separate from the original timeline. The original timeline continues unchanged, and no paradox arises because both versions of history coexist independently. This connects to the many worlds interpretation of quantum mechanics, where every possible outcome exists in some branch of reality. Under the branching view, you could save your grandfather from death, but you would arrive in a new timeline where he lived, separate from your original. The original timeline, where he died and you traveled back, still exists, unchanged by your actions in the new branch. You cannot really change the past, only create alternate versions of it that diverge from your starting point. This resolves the paradox by multiplying realities, giving each history its own separate existence. These resolutions are speculative and remain hotly debated because we have no evidence that backward time travel is possible at all. The paradoxes might simply show that such travel is impossible, that the laws of physics properly understood forbid it absolutely. Or the resolutions might point toward deep truths about consistency and reality, revealing how the universe handles situations that seem contradictory. We do not know which view is correct, and the question remains at the frontier of physics and philosophy. There is another fundamental question about backward time travel: whether the past still exists as a destination for travelers to reach. In the presentist view, only the present moment is real, and the past has vanished into non-existence, gone beyond recall. If the past no longer exists, you cannot travel there any more than you can travel to a place that does not exist. The past would be like a room that has been demolished. There is nowhere to go because the destination is simply gone. But the block universe view, suggested by relativity, paints a different picture, with all of time existing eternally in a four-dimensional block. If this view is correct, the past still exists, as real and present as the moment you are experiencing now. It is located at different coordinates in the block, just as distant places are located at different spatial coordinates. In this view, traveling to the past is at least conceptually coherent, a journey to a region of space-time that genuinely exists. Most physicists who take backward time travel seriously adopt some version of eternalism, the view that past, present, and future all equally exist. This is the natural interpretation of special and general relativity, where time is just another dimension, not fundamentally different from space. If space persists even where we are not looking, why should time not persist even when it is past from our perspective? The block universe makes time travel a matter of navigation, finding a path through space-time that connects different temporal locations. The path required for backward time travel cannot be an ordinary path, because ordinary motion always carries us forward in time, never backward. We would need an exotic path, a closed time-like curve that loops back on itself, returning to an earlier moment. Whether such paths exist in our universe is an open question, and finding solutions to Einstein's equations that contain them is a focus of theoretical research. We will explore these exotic possibilities in the next part, looking at wormholes and other structures that might allow travel to the past. For now, rest with the understanding that backward time travel faces serious obstacles, paradoxes that threaten logical consistency, and questions about whether the past exists. These obstacles might be insurmountable, forbidding travel to the past absolutely, or they might be resolved by subtle mechanisms we do not yet understand. The question remains open, an invitation to continued exploration at the boundaries of physics. In the next part, we will explore wormholes, tunnels through space-time that might connect different times and places. If you wanted to travel to a distant star without spending years on the journey, you might wish for a shortcut through space, a tunnel bypassing the normal route. General relativity suggests that such tunnels might be possible in principle, structures called wormholes that connect distant points through curved space-time. And if a wormhole can connect distant points in space, perhaps it can also connect distant points in time, allowing travel to the past. Tonight we explore these hypothetical tunnels and ask whether they could serve as time machines. The concept of a wormhole emerged from Einstein's own work with Nathan Rosen when they studied solutions to the field equations that had unusual properties. In 1935, they found that the geometry around a black hole could be extended to connect to another region of spacetime far away. This Einstein-Rosen bridge, as it was called, seemed to offer a shortcut between distant locations in the universe. But they quickly realized that this particular bridge was unstable, pinching off too quickly for anything to pass through. The modern concept of a traversable wormhole was developed much later, in the 1980s by Kip Thorne and his colleagues at Caltech. Thorne was asked by his friend Carl Sagan for a scientifically plausible way to travel faster than light for Sagan's novel Contact about alien communication. Thorne and his students worked out what would be required for a wormhole to stay open long enough for travelers to pass through. What they found was surprising and important. Traversable wormholes require exotic matter with negative energy density. Exotic matter is not like ordinary matter, which always has positive energy. It would have strange properties that violate conditions normally assumed in physics. In particular, it would have to create repulsive gravity, pushing outward instead of pulling inward like normal matter. This repulsion would be needed to hold the wormhole open, preventing it from collapsing under its own gravitational dynamics. Without exotic matter, the wormhole would pinch off instantly, crushing anything that tried to pass through. Does exotic matter exist? And could we obtain enough of it to stabilize a wormhole? These are open questions at the frontier of physics. Some quantum effects do produce small amounts of negative energy, like the Casimir effect between closely spaced metal plates. But the amounts are tiny, and whether they could be amplified to stabilize a macroscopic wormhole is unknown. Most physicists are skeptical that enough exotic matter could be gathered, but the question is not settled and research continues. If we could somehow create and stabilize a traversable wormhole, it could function as an instant transportation device connecting distant places. You would enter one mouth of the wormhole, pass through a short tunnel of distorted space-time, and emerge from the other mouth far away. The journey through the wormhole might take only seconds, even if the mouths were separated by light years of ordinary space. This would not technically be faster than light travel, because through the wormhole, the distance is actually short. But here is where time travel enters the picture. Because a wormhole connecting distant places could also connect different times. Imagine you create a wormhole with both mouths near Earth. Then you take one mouth on a high-speed journey while leaving the other behind. Due to time dilation, the traveling mouth would age less, experiencing less time than the stationary mouth during the journey. When you brought the mouths back together, they would be connected through the wormhole, but separated in time. If you entered the stationary mouth, you would emerge from the traveling mouth, which, from your perspective, is in the past because it has aged less. And if you entered the traveling mouth, you would emerge from the stationary mouth, which, from that perspective, is in the future because it has aged more. The wormhole would have become a time machine, connecting two different times through its distorted internal geometry. This is not speculation, but a consequence of combining wormhole physics with special relativity, two well-established theories that together imply this possibility. Of course, this time machine would have important limitations. You could not travel back to before the wormhole was created and separated. It would only connect times from the creation moment forward. So you could not visit the dinosaurs or prevent historical disasters from before the machine existed. And all the problems of exotic matter would still apply. You would need enormous amounts of negative energy density to stabilize the structure. But within these limits, the physics seems to allow it. A genuine time machine built from the fabric of space-time itself. Thorne and his colleagues also explored whether wormhole time machines would be stable, or whether quantum effects would destroy them before they could be used. They found troubling signs that vacuum fluctuations might build up, growing stronger and stronger as they cycled through the time machine's loop. These fluctuations might create infinite energy at the chronology horizon, the boundary at which closed time-like curves first appear. This could destroy the wormhole just as it becomes a time machine, or create a singularity that blocks travel through it. Stephen Hawking took this as evidence for his chronology protection conjecture, the idea that physics conspires to prevent time machines from forming. The vacuum fluctuations would act as a self-destruct mechanism, triggered whenever the geometry approaches the critical configuration. Hawking admitted he could not prove this conjecture, but he suspected the universe would protect itself from the paradoxes that time travel creates. The wormhole might be possible as a space bridge, but not as a time bridge, with quantum effects drawing the line. However, the calculations are incomplete and the conclusion uncertain, because we do not have a full theory of quantum gravity to analyze the situation. The behavior of vacuum fluctuations near a chronology horizon depends on quantum effects in strongly curved space-time, where our theories are weakest. Different approaches give different answers, and some researchers believe wormhole time machines might survive the quantum effects after all. The question remains open, awaiting better theories and perhaps future insights that will settle the debate. The image of a wormhole is often depicted as a tunnel through folded space, connecting two points on a sheet that has been bent to bring them close. This is a two-dimensional analogy for three-dimensional space, where the sheet represents space and the fold brings distant regions together. The tunnel itself goes through a higher dimensional bulk, a shortcut that bypasses the long route across the surface. Whether our universe actually has such a bulk is unknown, but the mathematics of general relativity allows solutions with wormhole geometry. No wormhole has ever been observed, and we have no evidence that they exist, but the theoretical possibility remains open, consistent with known physics. Perhaps wormholes form naturally in the universe, remnants of the Big Bang or products of exotic conditions we do not understand. Perhaps advanced civilizations have learned to create them, engineering space-time itself into tunnel structures for transportation. Or perhaps they are impossible for reasons we have not yet discovered, forever confined to the pages of theoretical physics papers. For tonight, rest with the image of a wormhole as a bridge through space-time, a tunnel connecting different places and possibly different times. The physics is speculative but serious, worked out by some of the greatest minds in general relativity. Whether such tunnels can exist remains unknown, but contemplating them expands our sense of what reality might allow. In the next part, we will explore other exotic structures, rotating black holes and cosmic strings that might also permit time travel. Wormholes are not the only exotic structures that might allow time travel. General relativity contains other solutions with strange temporal properties. Tonight we explore two of these, rotating black holes and cosmic strings, each offering different paths to the past that physicists have seriously considered. These are not practical blueprints for building a time machine, but they reveal how flexible space-time can be and what the equations allow. Black holes are among the strangest objects in the universe, regions where gravity has become so intense that nothing can escape, not even light. But not all black holes are the same. and rotating black holes have properties even stranger than their non-rotating cousins. These spinning giants, described by the Kerr solution to Einstein's equations, might offer pathways through spacetime that non-rotating black holes cannot provide. Tonight we explore these exotic possibilities, the physics of rotating black holes and cosmic strings as potential time machines. When a massive star collapses to form a black hole, it usually carries angular momentum, the spin from the star's original rotation, which cannot simply disappear. This means most black holes in the universe are probably rotating, spinning at tremendous speeds that drag space-time itself around with them. The physicist Roy Kerr found the mathematical solution for rotating black holes in 1963, and his equations revealed something remarkable about what lies inside them. Unlike the simple point singularity of a non-rotating black hole, a Kerr black hole has a ring-shaped singularity with very different properties. The ring singularity of a rotating black hole is not a point, but a circle, a loop of infinite density and curvature around which space-time is twisted. This ring shape opens possibilities that point singularities do not, because you might be able to pass through the center of the ring without hitting the singularity itself. In the mathematics of general relativity, passing through the ring leads to another region of space-time entirely, perhaps another universe or another time. This is purely theoretical, and immense practical obstacles stand in the way. But the equations suggest that rotating black holes are more than just cosmic dead ends. The region around a rotating black hole is called the ergosphere, a zone where space-time is dragged so powerfully that nothing can remain stationary. Even light in the ergosphere must rotate with the black hole, carried along by the current of twisted space-time. This frame-dragging effect has been measured around Earth, which also rotates, though Earth's effect is incredibly weak compared to a black hole's. The ergosphere represents a region where the normal rules of space and time become distorted in ways that might permit unusual journeys. Some theoretical physicists have speculated about using rotating black holes for time travel, entering in one location of space-time and emerging in another. The mathematics suggests that passing through the ring singularity could connect to regions where time runs differently, or even backward. Roger Penrose proposed mechanisms for extracting energy from rotating black holes, and others have imagined using these properties for more exotic purposes. But the practical challenges are overwhelming. The tidal forces would tear any spacecraft apart, and we do not know if the internal structure survives in real black holes. Real black holes, as opposed to idealized mathematical solutions, are surrounded by chaotic environments of infalling matter and radiation that complicate the picture. The elegant Kerr geometry might be unstable against small perturbations, collapsing into something simpler and less useful when anything actually enters. This is an active area of research, with physicists debating whether the interior geometry of rotating black holes is stable enough for traversal. The mathematical possibility does not guarantee physical reality, and nature might close these loopholes before any time traveler could exploit them. Cosmic strings are entirely different objects, hypothetical defects in the fabric of space-time, left over from the early universe when different phases of space froze unevenly. Imagine water freezing into ice, with cracks forming where crystals meet. Cosmic strings would be like cracks in space-time itself, incredibly thin but carrying enormous energy. These strings, if they exist, would stretch across cosmic distances, thinner than an atom but with the mass of mountains packed into every meter. The gravitational effects of cosmic strings would be bizarre, warping space-time in ways that differ from ordinary matter. The physicist J. Richard Gott proposed in 1991 that cosmic strings might enable time travel if two strings passed by each other at very high speeds. The space-time around a cosmic string is not curved in the usual way. It is conical, with missing angles like a pie with a slice removed. When two such strings pass each other at relativistic speeds, the combined distortion of space-time might create closed time-like curves. A spacecraft following the right trajectory around the passing strings might return to its own past by exploiting the warped geometry. The energy requirements for the Gott time machine are extraordinary. The strings would need to be moving at nearly the speed of light. The total energy involved would be comparable to the mass energy of an entire galaxy, far beyond any technology we can imagine, even in principle. And we do not know if cosmic strings exist at all. Searches for their gravitational signatures in the cosmic microwave background have found nothing definitive. They remain theoretical possibilities, predicted by some models of the early universe, but not confirmed by any observation we have made so far. Another idea involving extreme rotation comes from the physicist Frank Tipler, who proposed that an infinitely long, rapidly rotating cylinder could create closed, time-like curves. The Tipler cylinder would need to spin at tremendous speed, dragging space-time around it so powerfully that time itself loops back. A spacecraft spiraling around the cylinder in the right direction might travel into its own past by following the twisted geometry. The idea is mathematically sound within general relativity, but requires an infinitely long cylinder, which is obviously impossible to construct. Even a finite cylinder would not work for the Tipler time machine. The ends of the cylinder would create complications that prevent the closed time-like curves from forming. Stephen Hawking analyzed Tipler's proposal and found fundamental limitations, supporting his chronology protection conjecture that nature forbids time travel. The pattern repeats across many proposed time machines. They work in idealized mathematics, but face insurmountable obstacles when made realistic. This does not mean time travel is proven impossible, but it suggests that the universe may have built-in protections against it. The physics of rotating systems reveals deep connections between space, time, and motion. Connections that Einstein first uncovered with his theories of relativity. Rotation drags space-time, creates frame effects, and in extreme cases might twist time itself into unusual configurations. These are not fantasies, but consequences of well-tested physics. Predictions of equations that have been confirmed in countless other applications. The question is whether nature allows these extreme cases to occur, or whether other physics intervenes before time travel becomes possible. Black holes themselves have been detected through gravitational waves and direct imaging, so we know that extreme gravity exists in the universe. The Event Horizon Telescope captured the first image of a black hole's shadow in 2019, confirming that these objects are real and match our theoretical predictions. Whether their interiors contain traversable passages to other times remains unknown and perhaps unknowable from our position outside the horizon. The information that would tell us what lies inside cannot escape to reach our telescopes and instruments. As you rest with these ideas of rotating black holes and cosmic strings, let the strangeness become familiar through gentle contemplation. These are the most extreme objects physics can describe, pushed to limits where our understanding becomes uncertain. The mathematics allows time travel in principle, but nature may have other plans for what actually occurs. In the language of physics, a path through spacetime is called a world line, tracing where an object has been and where it is going through both space and time. Normally, world lines move relentlessly forward in time, even as they wind through space in various directions. But some solutions to Einstein's equations contain something remarkable: paths called closed time-like curves that loop back on themselves. These mathematical objects represent the most direct form of time travel, and understanding them reveals deep truths about space-time and causality. A closed time-like curve is exactly what its name suggests: a timeline that forms a closed loop connecting back to its own beginning. If you traveled along such a curve, you would eventually return to the exact moment and place where you started, meeting your earlier self. This is not travel through space that brings you back to the same location, but travel through time that brings you back to the same moment. The existence of such curves in general relativity was one of the most surprising discoveries in the history of physics. The first person to find closed time-like curves in Einstein's equations was Kurt Gödel, the brilliant logician who was Einstein's friend and walking companion at Princeton. In 1949, Gödel discovered a solution describing a rotating universe, where matter spins around a central axis and drags space-time with it. In this Gödel universe, the rotation is so extreme that world lines can curve around and return to their starting point in time. Gödel presented this discovery as a birthday present to Einstein, who was reportedly disturbed by the implications for time and causality. The Gödel universe does not describe our actual cosmos, because our universe is expanding, but not rotating in the way Gödel imagined. Observations of the cosmic microwave background show no evidence of universal rotation, so the Gödel solution is a mathematical curiosity, rather than a description of reality. But its existence proves something important about general relativity. The theory allows for closed time-like curves under certain conditions. If one solution permits time travel, others might too, and physicists have found several other spacetimes containing these loops. The mathematics of closed time-like curves is straightforward in general relativity. They appear when the metric of spacetime has certain properties that allow world lines to close. Near a rotating black hole, close to certain configurations of cosmic strings, or in spacetimes with exotic matter, these curves can form. The equations do not forbid them. They emerge naturally from the same principles that describe ordinary gravity and motion. This is what makes time travel such an interesting question for physics. It is not ruled out by the basic laws we have discovered. What would it be like to travel along a closed time-like curve, to experience a loop in time from the inside? From your perspective, everything would seem normal. You would age, think, act in ordinary ways as you traveled. But eventually, you would arrive back at your starting point, meeting yourself as you were about to begin the journey. The two versions of you would be the same person at different stages of the loop, a single world line that intersects itself in time. This is profoundly strange to imagine, that the mathematics describes it without contradiction. The real question is whether such loops could form in our actual universe, whether the conditions for closed time-like curves could ever be created. Every proposed mechanism requires exotic circumstances: rotating black holes, cosmic strings, wormholes held open by negative energy, None of these are available to current technology, and some may be impossible according to physics we do not yet understand. The gap between mathematical possibility and physical reality is where the debate about time travel resides. Closed time-like curves create apparent paradoxes that have troubled physicists and philosophers, puzzles about causality and consistency that seem to undermine logic itself. If you can return to your own past, you could theoretically change events, altering what happened in ways that contradict your own existence. How can the universe allow paths that seem to permit logical contradictions, or does something prevent paradoxes from actually occurring? These questions connect the physics of spacetime to deep issues in philosophy and logic about the nature of reality. One approach to these paradoxes is the Novikov self-consistency principle, proposed by physicist Igor Novikov in the 1980s. This principle states that any events on a closed time-like curve must be self-consistent, that physics conspires to prevent paradoxes from ever forming. If you tried to change the past, something would always intervene. Events would unfold in ways that maintained consistency, perhaps in surprising ways. The universe would protect itself from contradiction, ensuring that history remains coherent even with time loops present. Another approach invokes the many worlds interpretation of quantum mechanics, suggesting that changing the past creates a new branch of reality. In this view, you cannot create a paradox because you never change your own past. You simply enter a different timeline where events unfolded differently. The grandfather paradox dissolves because killing your grandfather sends you to a branch where you were never born, leaving your original timeline intact. This multiplies realities but preserves logical consistency in each one. The physics of closed time-like curves remains an active area of research, with physicists exploring both their possibilities and their limitations. Some recent work uses quantum mechanics to analyze what would happen if particles or information traveled along time loops. These studies suggest that quantum effects might smooth out paradoxes or might create instabilities that prevent the loops from forming. The intersection of quantum mechanics and general relativity is precisely where we need new physics to fully understand time travel. What strikes many physicists about closed time-like curves is their mere existence in the equations, the fact that well-tested physics allows for such strange possibilities. General relativity is not some speculative idea. It is confirmed by GPS satellites, gravitational wave detectors, and countless other observations. That such a solid theory permits time loops is remarkable, suggesting that time is stranger than our everyday intuition imagines. Whether the loops are physical or merely mathematical remains open, but the question itself teaches us about the nature of time. The distinction between past, present, and future feels absolute to us. We remember the past, experience the present, and anticipate the future. But physics suggests this distinction may be partly illusory, that time is woven into space-time in ways that challenge our perceptions. Closed, time-like curves, if they exist, would make this explicit, showing that the past is not gone, but still present in the fabric of space-time. This connects to deep questions about the nature of existence, whether all moments are equally real or whether only the present exists. As you rest with these ideas of loops in time, let the paradoxes become puzzles rather than problems. The universe may have ways of resolving contradictions, ways we do not yet understand, but that maintain coherence. Time may be stranger than we imagine, and contemplating its strangeness is a worthy meditation. Time travel to the past creates paradoxes that seem to undermine logic itself, contradictions that have puzzled physicists, philosophers, and science fiction writers alike. These paradoxes are not mere storytelling devices. They represent genuine problems for any physics that permits travel to earlier times. Tonight, we explore these paradoxes in depth and the surprising ways that physics might resolve them without forbidding time travel entirely. The most famous paradox is the grandfather paradox, which we touched on earlier, but it deserves deeper examination for what it reveals about causality. Suppose you travel back in time and prevent your grandfather from meeting your grandmother. Then your parent would never be born, and neither would you. But if you were never born, you could not have traveled back to interfere. So your grandfather would meet your grandmother, and you would be born. Then you would travel back and prevent the meeting again, creating an endless loop of contradiction with no consistent resolution. The paradox seems to demand that time travel be impossible, that physics must forbid any path that could lead to such contradictions. Many physicists accept this conclusion, arguing that chronology protection prevents closed time-like curves from forming in any realistic situation. But others have proposed ways the universe might allow time travel, while still maintaining logical consistency through subtle mechanisms. These proposals show that paradoxes might not be as fatal to time travel as they first appear. The Novikov self-consistency principle offers one elegant resolution, stating that events on a closed time-like curve must form a consistent loop. In this view, you could travel to the past, but you would be unable to change anything that contradicts your own existence. If you tried to shoot your grandfather, the gun would jam, you would miss, or some other event would prevent the paradox from occurring. The universe would guide events toward consistency, not through magic, but through the ordinary physics of how events unfold. This might sound like a restriction on free will, a cosmic force preventing you from acting freely, but Novikov and others argue it is no different from other physical constraints. You cannot walk through walls or travel faster than light either. The laws of physics constrain what is possible, and if time travel exists, the laws would constrain it to prevent paradoxes. You would still feel free, still make choices, but the outcomes would always be self-consistent, woven into a coherent loop. Consider a modified scenario where you travel back and try to prevent your grandfather, but in doing so, you accidentally cause the very meeting you intended to stop. Perhaps you bump into your grandmother while chasing your grandfather, and she notices your grandfather because of the commotion you created. Your attempt to prevent the meeting caused the meeting. A consistent loop where your time travel was always part of the history. This kind of predestination loop is common in time travel stories, and it represents one way physics might enforce consistency. The bootstrap paradox presents a different kind of puzzle, concerning objects or information that seem to have no origin. Imagine you receive a book from your future self who traveled back to give it to you. Then you keep the book for years, age normally, and eventually travel back to give it to your younger self. Where did the book come from? Who wrote it originally if it has always existed in this loop? The book seems to have no author, no origin, no moment of creation, existing eternally in a self-sustaining cycle of cause and effect. Some physicists find bootstrap paradoxes less troubling than grandfather paradoxes because they do not involve logical contradictions, just strange causal structures. The book exists. It is real and consistent. It simply has an unusual history that loops back on itself. This might violate our intuitions about causation, but intuition is not always a good guide to how the universe works. Physics often reveals that reality is stranger than common sense suggests, and bootstrap paradoxes might be acceptable if time travel is possible. The information paradox of time travel raises questions about where knowledge comes from. If you learn something from your future self, who learned it from their future self? The information seems to emerge from nowhere, created by the loop itself, which troubles physicists who study thermodynamics and entropy. Information normally requires energy to create and process, so self-creating information might violate fundamental conservation laws. This is an active area of research, connecting time travel to deep questions about information in physics. The many worlds interpretation of quantum mechanics offers a different resolution to paradoxes by allowing multiple timelines to coexist without contradiction. In this view, when you travel back and change something, you create a new branch of reality where events unfold differently. Your original timeline continues unchanged with your departure, while the new timeline develops from your arrival and actions. There is no paradox because you never change your own past. You simply create and enter an alternative history. This many worlds approach is popular in science fiction, and it has some basis in actual physics, particularly quantum mechanics. The many worlds interpretation was proposed to explain quantum measurement, and it naturally extends to time travel if closed time-like curves exist. Each time travel event would spawn new branches, multiplying realities but preserving consistency in each one. Your grandfather lives in some branches and dies in others, but each branch is internally coherent without contradiction. Quantum mechanics might play other roles in resolving time travel paradoxes, roles that physicists are still exploring through theoretical analysis. Some studies suggest that quantum effects near time machines would create instabilities that prevent paradoxes from forming. The energy fluctuations would grow without bound, destroying the time machine before any paradox could occur. This is related to Hawking's chronology protection conjecture, the idea that physics conspires to prevent closed time-like curves. Other quantum approaches use the concept of post-selection, where only consistent histories are allowed to occur. In this view, quantum mechanics naturally filters out paradoxical timelines, leaving only self-consistent loops as physically realized. The probability of paradoxical events becomes zero, not because of any force, but because of how quantum probabilities work. This is speculative, but mathematically coherent, offering another way physics might handle time travel without contradiction. The resolution of time travel paradoxes may require physics we do not yet understand, a quantum theory of gravity that unifies our best theories. General relativity permits closed time-like curves in certain spacetimes, while quantum mechanics suggests constraints on what information can do. The true answer may emerge only when we have a complete theory, a framework that combines gravity, quantum mechanics, and spacetime into one picture. Until then, paradoxes remain puzzles pointing toward deeper understanding. What the paradoxes teach us, regardless of whether time travel is possible, is how tightly woven causality is into the fabric of reality. We normally take for granted that causes precede effects, that the past determines the future in an orderly sequence. Time travel would challenge this assumption, introducing loops and complications that force us to reconsider what causality really means. Even if we never build a time machine, thinking about these puzzles deepens our understanding of time and existence. After exploring wormholes, rotating black holes, cosmic strings, and closed time-like curves, it is time to ask what physics actually says about time travel today. The theoretical possibilities are fascinating, but what do working physicists believe about whether time travel is possible? Tonight we examine the current scientific consensus, the open questions, and the reasons why most physicists are skeptical, while some remain intrigued. The most important point is that physics does not definitively forbid time travel. The equations of general relativity allow for closed time-like curves in certain spacetimes. This is not a loophole or an error in the theory. It is a genuine feature of our best description of gravity and spacetime. Rotating black holes, certain wormhole configurations, cosmic strings, all these contain time travel possibilities within Einstein's well-tested framework. The mathematics is clear even if the physics is strange. However, allowing something mathematically is different from allowing it physically, and there are strong reasons to doubt that time travel can actually occur. Every proposed time machine requires conditions that seem impossible to create. Exotic matter with negative energy, infinitely long cylinders, cosmic strings moving at near light speed. The gap between what the equations permit and what nature provides may be unbridgeable with any technology, now or ever. Stephen Hawking proposed the chronology protection conjecture in 1992, the hypothesis that the laws of physics prevent closed time-like curves from forming. Hawking observed that every proposed time machine seems to face obstacles, quantum instabilities that would destroy it before it could work. He suggested this was not coincidence, but a fundamental principle, that the universe protects chronology from the paradoxes time travel would create. This remains a conjecture, not a proven theorem, but it captures the skepticism many physicists feel. The energy requirements for any proposed time machine are staggering, far beyond what any technology could provide. Wormholes would require negative energy to stay open, and while quantum effects can produce small amounts of negative energy, the quantities needed are astronomical. The Casimir effect shows negative energy exists in tiny amounts between metal plates, but scaling this up to wormhole sizes seems impossible by many orders of magnitude. The universe may simply not provide the resources for the engineering that time travel would require. Quantum effects near potential time machines pose another fundamental challenge, creating feedback loops that would generate infinite energy densities. When quantum fields interact with closed time-like curves, they can circle the loop multiple times, amplifying without bound. This back reaction would likely destroy any forming time machine, preventing the closed curves from ever becoming traversable. The calculation involves quantum field theory in curved spacetime, and it consistently shows instabilities that make time machines self-defeating. There is also the simple observation that we have never seen time travelers. No visitors from the future have appeared with advanced technology or historical knowledge. If time travel will ever be possible at any point in the future, we might expect some evidence of travelers coming back to our era. The absence of such evidence is not definitive proof. Perhaps time travel only reaches back to when the time machine was created, not before. But it adds to the circumstantial case that time travel may be forever beyond reach. The difference between traveling to the future and the past remains crucial, because future travel is already confirmed by physics, while past travel is not. Time dilation due to speed and gravity is measured and real. Astronauts age slightly less than people on Earth. Clocks on satellites run at different rates. Building a practical future time machine is an engineering challenge, not a physics mystery. We would need enormous speeds or extremely strong gravity, but no new physics. Past travel is fundamentally different, requiring mechanisms that may not exist in nature. Some physicists argue we should remain humble about what is possible, acknowledging that our current theories are incomplete. General relativity and quantum mechanics have not been unified, and a future quantum gravity theory might change everything we believe about spacetime. Perhaps that theory will confirm chronology protection as a fundamental law, or perhaps it will reveal mechanisms for time travel we cannot currently imagine. The history of physics is full of surprises, and certainty about what is impossible has often been proven wrong. Others argue that the consistent failure of every time travel proposal is significant, that the pattern of obstacles suggests a deep principle at work. When every door you try is locked, eventually you suspect the room is sealed, and perhaps time travel is sealed off by the structure of physics itself. The chronology protection conjecture, even if not proven, may reflect a truth about how the universe maintains causality. The past may simply be unreachable, a one-way destination that we can never return from once we have left. The study of time travel is not useless even if travel proves impossible, because it teaches us about the structure of space-time and causality. The questions we ask about closed time-like curves reveal deep connections between gravity, quantum mechanics, and information. Physicists learn about their theories by pushing them to extremes, and time travel is the ultimate extreme test for theories of space and time. Even negative results have value, showing what the theories do and do not permit. For practical purposes, you should not expect a time machine in your lifetime, or in any foreseeable future based on current physics. The obstacles are not like the obstacles to building airplanes or computers, where we understood the physics and needed only better engineering. The obstacles to time travel may be fundamental, built into the laws of nature, barriers that no technology can overcome, regardless of how advanced. This is the honest assessment of most physicists. Time travel to the past is probably impossible and certainly not near. But the qualifier probably matters, because physics has surprised us before and may surprise us again. A century ago, nuclear energy and quantum computers were unimaginable, technologies that seemed to violate the physics that was then understood. New theories revealed new possibilities, and the same could happen with quantum gravity and time travel. We should hold our conclusions with appropriate humility, acknowledging that the future of physics is unknown. What remains clear is that time travel raises profound questions about the nature of reality. Questions worth asking even if the answer is that travel is impossible. Why does time seem to flow in one direction? What distinguishes past from future at the fundamental level? These questions connect physics to philosophy, consciousness, and the human experience of temporality, enriching our understanding of what it means to exist in time. We have traveled far tonight, through the physics of time and the dream of time travel, from Einstein's relativity to wormholes, from paradoxes to the limits of what physics allows. Now, as our journey draws to a close, let us gather what we have learned and let it settle gently into awareness. Time may not be what we thought it was, and contemplating its mysteries can bring a kind of peace that transcends the answers we do or do not find. The most fundamental thing we have learned is that time is not simple. Not the absolute background that Newton imagined, ticking uniformly everywhere. Time is woven into space-time, stretched by motion, bent by gravity, a dynamic part of the universe that participates in physical events. Clocks in different places and states of motion tick at genuinely different rates, and this is not illusion, but the actual nature of time itself. The universe is stranger than our everyday intuition suggests, and that strangeness is beautiful when you let it settle into your understanding. We are all time travelers, moving constantly into the future at a rate of 1 second per second under normal conditions. But even this baseline rate can be changed by motion and gravity. Astronauts age slightly less than their twins on Earth. Clocks at sea level lag behind clocks on mountains. These effects are tiny in everyday life, but they prove that time is malleable in ways that matter. The future is a destination we are all approaching, and physics shows we can influence the pace of our approach. Traveling to the past, by contrast, remains beyond our reach and may be forbidden by the deepest principles of physics. Every proposed mechanism faces overwhelming obstacles. Exotic matter we cannot create, energy scales we cannot achieve, instabilities that would destroy any time machine. The chronology protection conjecture suggests the universe protects itself, maintaining causality against the paradoxes that backward time travel would create. The past may be a country from which no traveler returns, a destination visible only in memory and history. Yet the question of time travel has taught us much about the nature of time, revealing connections between gravity, quantum mechanics, and causality that we might not otherwise have noticed. The paradoxes forced us to think carefully about cause and effect, about what it means for events to be ordered in time. The mathematics of closed time-like curves illuminated the structure of space-time, showing what the equations permit even if nature does not. The journey has been valuable, regardless of whether the destination of time travel is ever reached. There is something liberating about accepting the flow of time as it is, moving forward without the burden of wishing we could change the past. The past has shaped us, given us memories and experiences, but it is complete now, settled into the structure of what has been. We cannot go back to fix our mistakes or relive our joys, but we can carry the lessons forward into a future that remains unwritten. The present moment is where we live, the only time where action is possible, where change can happen. Every moment you experience is a kind of time travel into the future, a journey that moves at the pace of one heartbeat after another. You are crossing time right now, moving through it as you rest, your cells aging imperceptibly, your thoughts flowing from one to the next. This journey is the most fundamental thing we do, more basic even than breathing, which only happens because time passes. To exist is to travel through time, and in this sense, we are all already time travelers. The future that awaits you is unknown, full of possibilities not yet determined, moments that will become your memories, experiences that will shape who you are. You cannot visit that future and return to tell yourself what you learned, but you will get there eventually, one moment at a time. The anticipation of the future gives life its sense of openness, the feeling that anything might happen, that change is possible. This openness is a gift that the forward flow of time provides. The mystery of why time flows forward remains unsolved. one of the deepest puzzles in all of physics and philosophy. Entropy increases, the second law of thermodynamics says. Disorder grows, and this gives time its arrow. But why this particular direction? Why not the reverse? These questions touch on the initial conditions of the universe itself. The Big Bang set time flowing in the direction we experience, and we are still riding that wave, billions of years later. Consciousness and time are deeply intertwined in ways we do not fully understand. Our experience of the present moment, the feeling of now, remains mysterious. Physics describes time as a dimension, coordinates in equations, but experience presents time as flowing, as moving, as passing. This gap between physics and experience is one of the great unsolved problems at the intersection of science and philosophy. Perhaps future understanding will bridge this gap, or perhaps the mystery will endure as part of what it means to be conscious. Tonight, as you drift towards sleep, time will continue its quiet work, carrying you from wakefulness into dreams, from today into tomorrow. Your body will repair and restore itself during sleep, processes that unfold through time, taking the hours they need. The Earth will continue rotating, bringing the sun back around, and you will wake to a new day that exists because time has passed. Sleep is a small journey through time, a few hours that transport you to the morning. The universe itself is a time traveler on the largest scale, expanding and evolving over billions of years. Stars are born and die, galaxies collide and merge, all of it unfolding through the dimension of time that physics has revealed. The cosmic microwave background shows us light from the early universe, a message that traveled through time to reach our telescopes. We see the past when we look at the night sky, light that left distant stars years or centuries or billions of years ago. And here you are, a brief pattern in cosmic time, a conscious being experiencing the flow of moments. The atoms in your body were forged in ancient stars, and they will return to the cosmos long after you are gone. But right now, in this moment, they are you, arranged in a pattern that thinks, feels, wonders about time travel. This is remarkable when you let yourself feel it, the improbability and preciousness of this moment of awareness. There is peace in accepting the flow of time as it is, not fighting against it or wishing it were different than it is. The past is complete, the future is open, and the present is where you are, the only moment you can actually inhabit, the only time you can act. Mindfulness traditions have long taught the value of presence, and physics confirms that the present moment is genuinely special, the edge of time where things happen. Let go now of the complex ideas we have explored tonight, the wormholes and black holes, the paradoxes and equations that describe space-time. Let them settle into memory as interesting thoughts, ideas that enriched your understanding but do not need to be held tightly. The universe will continue whether you think about it or not, and sleep is a time for rest, not analysis. The mysteries will still be there when you wake, patient and vast, waiting for curious minds to explore. Your body is relaxing now, your breath slowing, time doing its quiet work of carrying you towards sleep and restoration. The room around you is still, the night is deep, and you are safe in this moment, held by the ordinary passage of time. There is nowhere you need to go, nothing you need to do. Just rest and let time carry you gently into dreams. The stars outside, if you can see them, are ancient light, photons that left their sources years or centuries ago, finally arriving at your eyes. You are connected to that vast universe through time, through the light that travels across the cosmos to reach you. And you are connected to the future, through the moments that will unfold from now into tomorrow and beyond. You are woven into time, a beautiful thread in the tapestry of cosmic history. Thank you for joining me on this journey through the physics of time and time travel, for letting these ideas accompany you toward rest. I hope they have brought wonder and peace in equal measure, a sense of connection to the deep mysteries of existence. Time is strange and beautiful, and thinking about it is one of the great privileges of having a curious mind. From all of us here at the Drowsy Astronaut, we wish you a peaceful night and restful sleep. May your dreams carry you gently through the hours, and may you wake refreshed, ready for the new day that time will bring. The flow of time is carrying you now into sleep and restoration, into the quiet that follows a long journey. Good night, fellow traveler through time. May the moments ahead bring you peace and renewal. The universe is vast and ancient, and you are part of its story, resting now in the eternal flow. Let go of waking thoughts, and let time carry you softly into dreams. Sleep well, and may time be gentle with you tonight and always.